Greetings, everybody. Welcome back to Learning as a Hobby. As promised in this video, I'm gonna do the exercises for the Chapter 4 exercise set in Spivak's calculus. So I'll do the selected exercises from Chapter 4 in this video. The next one, I'll do the summary for Appendix 1, then the exercise set for that. Then, Appendix 2, the exercise set for that, and then Appendix 3 and the exercise set for that. Those will be probably on the weekend. So hopefully by the end of the week, we should be finished with Chapter 4 in Spivak, and we can move on to the actual calculus part of the book Calculus, which starts in Chapter 5. So yeah, we're going to go over the exercises or selected exercises from Chapter 4 in this video. Before I do that, let me just apologize for my sniffling. I think my allergy season is starting, so I am a bit sniffly today, so I apologize for that. If you hopefully it doesn't bother you too much hearing me sniffle during the video. But okay, let's just jump into the exercises. So let me bring up my notes here. I mean, my solutions. All right, let's start with number 2. So like I said, I only did problems. There's a lot of problems in this section. I think there's like 23 problems, and they all have like a bunch of parts. So I only did ones that looked particularly interesting to me, or that looked looked important for stuff that we might need later on. So I started with question number 2. Let me just read it out, and then we'll go through the solution. Before I do that, I'm just going to move this video up into the corner. Okay. So here we go. Number 2. There's a very useful way of describing the points of the closed interval from A to B, where we assume, as usual, that A is less than B. There's I think 4 parts to this, so we'll take them one at a time. Part A says, first consider the closed interval from from 0 to B for B greater than 0. Prove that if X is in the closed interval from 0 to B, then X equals TB for some T with T between 0 and 1. And then he wants us to say what the significance of the number T is. So let's go through that one first, and then we'll look at the other examples in turn. Okay, so part A. So direct proof. So here, assume that X is in the closed interval from 0 to B. Then that means that by the definition of what it means to be in that interval, X is between 0 and B. So, X is greater than or equal to 0, less than or equal to B. Then since B is greater than 0, we can divide all sides of that triple inequality by B. And that gives us this inequality: 0 less than or equal X over B less than or equal to 1. So we could choose T to be the number X over B. Then if you multiply B by that number, then you get the number X. So that's what, so you can get any number in the interval from 0 to B by doing that. All right. And then the significance of T is it's a scaling factor. Okay. Part B. Now prove that if X is in the closed interval from A to B, then X is of the form 1 minus T times A plus TB for some T with T between 0 and 1. He gives a hint here. This expression can also be written as A plus T times B minus A. And then once we do that part, then he wants us to say what the midpoint of the interval is and what is the point 1/3 of the way from A to B. So let's do that one next. All right, so again, let X be in the closed interval from A to B. That means that X is greater than or equal to A and less than or equal to B. If you subtract A from all 3 sides of that inequality, you get 0 is less than or equal to X minus A, less than or equal to B minus A. Okay, which since that means that X minus A is in the interval from 0 to B minus A. So from part A, that means that we can write X minus A as T times B minus A for some T between 0 and 1, right? That's what we already established in part A. Therefore, you can, to that equation, you can add A to both sides, and that gives you X is equal to A plus T times B minus A, which you can rearrange to 1 minus TA plus TB, just, distribute the T and combine like terms. For T between 0 and 1, and that shows that you can do that. The midpoint is just the average of A and B. In other words, it's using the formula that we just have. That's when T is 1/2, and the point 1/3 of the way from A to B is when t is 1/3, so you plug that in and you get that the point 1/3 of the way from A to B is the point 2A plus B all over 3, right? Parts C and D are relatively straightforward once you have the first two parts. Prove conversely that t between 0 and 1, sorry, if t is between 0 and 1, then 1 minus ta plus tb is in the closed interval from A to B. So let's do that one. So again, start with your hypothesis. Assume that t is between 0 and 1. And I actually don't need this part here, so I'll just cross that out. Then from this inequality here, multiply all three sides by b minus a, and that gives you this inequality here. And then all you have to do is add a to all three sides, and that gives you that a is less than or equal to 1 minus t a plus tb, because we can rearrange this to get that. And that's less than or equal to b, which is what we wanted to show, right? Part D is also straightforward. It's almost identical to part C. The points of the open interval AB are those of the form 1 minus t times A plus TB for t between 0 and 1. Here, we're excluding the endpoints because it's an open interval. It's virtually the identical to the proof that we just did in part C. So if t is between 0 and 1, multiply both sides by b minus A, then add A to all three sides, and you get what you want, right? And that's basically it. Okay, next one I did, it looks like, is question 6. So there's a few parts to this as well. Part A says, show that the straight line through the point AB with slope m is the graph of the function f of x equals m times x minus a plus b. This formula, known as the point slope form, is far more convenient than the equivalent version f of x equals mx plus b minus a ma. It is immediately clear from the point slope form that the slope is m and the value of f at a is b. If you recall, this form here is called the slope intercept form, and that's because this is actually the y-intercept. But we'll go through this in a second. So let me scroll down to part A, my solution to part A. So let L be the line with slope m passing through the point AB. So here I have the picture drawn. Here, this is the point AB, right? That's the point AB. And pick any other point on the line. For example, here I'm choosing the point XY. Then, since the slope of the line is a real number, meaning the line's not vertical, right? That means that x minus a is not 0. And from the picture, you can see that m is y minus b over x minus a. And then you could solve that for y, which gives you the point slope form, y equals m times x minus a plus b. And you can rearrange that to get the slope intercept form, right? Just to distribute the m and recombine things. That gives you the point slope form. You can see that these two things are identical from the geometry of the picture as well. Let me actually erase this and I'll describe what I have drawn in the picture here. All right, so the y-intercept is this point here. Notice that that's equal to the height b minus m times a, right? So the y-intercept here is b minus ma. Okay. Similarly, the height here, this one, is equal to so if this is x here, the height there is equal to m times x, right? So this large height here is mx, right? But you can see that from the triangle here, right? So if you take, let me just make this a little bit, why is this not erasing? Just make this a little bit clearer to see. So if you look, the green line segment here is b minus ma plus mx, so that the y coordinate here has that height, right? That's equal to this quantity here. But also you can write it as the height b, right? The height b plus, and then from the triangle here, you can see that this height is actually m times x minus a, because this distance is x minus a. So if you take b plus m times x minus a, you get the same y value. Sorry, not over here. You get the same y value. So these formulas give you the same height, right? So should be clear from the drawing that that's true as well. All right, that's, what was that, part A, I think it was, right? And there's a couple other parts to this problem. Part B says for A not C, show that the straight line through the point AB and then CD is the graph of the function f of x equals d minus b over c minus a times x minus a plus b. This is straightforward once we have part A established. So if A is not C, then the line is not vertical, right? So it has a slope. And from the picture, you can see that the slope is d minus b over c minus a. And you just plug that in for m in the formula, the point slope formula from part A, and that's it. That's all you have to do. Right, and then lastly, part C. Part C says, when are the graphs of f of x equals mx plus b and g of x equals m prime x plus b prime parallel straight lines, right? So here we go. So first off, the two lines are not parallel if they intersect at some finite point, right? Because if you remember, parallel lines, geometrically anyway, parallel lines are lines that never intersect, right? So let's figure out the cases where the two lines will intersect. So first off, if m is not m prime, meaning the slopes are different for the two lines, and and assuming that they intersect, right here, we get that there is an x value. Okay, so there's an x value where they intersect. This is a real number because m minus m prime is not 0, right? So they intersect if the slopes are different. In other words, there's a solution to this equation. Okay, the other case is if the slopes are equal. If m is m prime, then mx plus b equals m prime x plus b prime, if and only if b is b prime. That exhausts the two cases where the two lines intersect at a finite point. So if neither of those cases happen, then the lines are parallel. In other words, if m is equal to m prime and b is not b prime, that's the condition for a line with a slope to be, two lines with slopes to be parallel. Okay, that was part C. All right, next problem, part A. Prove that the graphs of the functions f of x equals mx plus b, g of x is nx plus c, are perpendicular if m times n is -1 by computing the square of the lengths of the sides of the triangle in the figure. So here, just so you can see, because I labeled the lengths of these triangles. I labeled the lengths of the sides of this triangle using different notation in the proof. So let me just write down what they are here. I called this L1, I called this L2, and the big length here I called L3. So going down to my solution for part A. So start with our hypothesis that m times n is -1. Then using the distance formula to calculate the lengths of the sides of that triangle, L1 has length square root 1 plus m squared, L2 has length square root 1 plus n squared, and L3 has length, when you simplify everything, m minus n. I guess technically it should be absolute value, but the way that we drew the picture, it looks like n is negative anyway, so this would always be a positive quantity. But obviously that's not true for every two lines. This is a general principle. Anyway, notice that if you square L3, that's equal to m minus n squared, which simplifies to give you m squared plus n squared minus 2mn when you multiply everything out. But remember, our hypothesis is that m times n is -1, so this simplifies to give you m squared plus n squared plus 2, which is exactly L1 squared plus L2 squared. Therefore, that means that the triangle satisfies the Pythagorean theorem, or in other words, it's a right triangle, and the angle that is the right angle is this one over here. So that means that the line L1 and the line L2 are perpendicular, right? So that's the answer for part A. Then part B says prove that, excuse me, prove that the two straight lines consisting of all x, y, satisfying the conditions ax plus by plus c equals 0, a prime x plus b prime y plus c prime equals 0 are perpendicular if and only if a prime plus b prime are 0. All right, this is a biconditional statement because of the if and only if, so we have to actually do this in both directions. We have to do the forward and the reverse direction. So let's do that. All right, so doing the forward direction first, let ax plus by plus c equal 0 and a prime x plus b prime y plus c prime equals 0 be perpendicular. Without loss of generality, we can assume that the first equation gives you a line that's vertical, and then in order for the two lines to be perpendicular, that's our hypothesis, then the other line has to be horizontal, right? And for these formulas, if the first line is vertical, that means that b has to be 0, and that means, and for the second line to be horizontal, that means that a prime has to be 0. So plugging that into the expression here, a prime plus b prime, that means that that's equal to a times 0 plus 0 times b prime, which obviously is 0. So that case works out. The next case, assume that neither line is vertical, then both lines have finite slope, slopes. And if you solve for each of the equation for y, the first equation gives you y is negative a over b x minus c over b, and the second equation gives you y equals negative a prime over b prime x minus c prime over b prime. Then by part A, that since we are assuming that the lines are perpendicular, if you take the product of their slopes, that should be equal to -1. And then just rearranging things using algebra, we get a prime plus b prime equals 0, so that case works out as well. All right. Now we can do the reverse direction. So here the hypothesis is that the formula is, that equation is satisfied, a prime plus b prime equals 0. Just rearranging things again, that shows that the product of a over b times a prime over b prime is -1. Just, by rearranging this, right? Bring b prime over to the right hand side, divide by b prime, and you get that equivalent equation there. And if we use this factor as the slope of a line here and use this factor as the slope of a line here, then the product of the slopes is -1. So by part A? That was the I already forgot when we did this in part A. That means that the two lines are perpendicular, and that's the proof. All right, next question. They want us to prove some inequalities. 9a says prove using problem 119. We actually did problem 119 way back a bunch of months ago. So if you want to see that problem, you can go back in the playlist for Spivak's calculus on the channel, and go to the videos on chapter 1. And in one of those videos we did the solution to 119. I don't remember which one it was, but you can look at that. If you don't remember, 119 was about the Cauchy-Schwarz inequality. So in that problem, we proved the Cauchy-Schwarz inequality. Or I think he just called it the Cauchy. Sorry, this should be Cauchy. I think he just called it the Cauchy inequality. I don't recall. But anyway, we did that problem a while back. So we're going to use that to show that this inequality is true. So let's actually do that first, and then we'll look at part B. What I did, just because working with square roots is not convenient, so I instead of working with instead of working the left-hand side with the square root, I started by looking at, I started by looking at the square of the left-hand side. Again, just to make the calculation a little bit easier. All right, so the square of the left-hand side is equal to x1 plus y1 squared plus x2 plus y2 squared. Multiply that out and rearrange things in this form here, which you can do. Then notice this is, I'm bringing these along for the ride here. The 2 comes along for the ride. But by problem 119, this part here is less than or equal to this part. So that's where Cauchy-Schwarz comes in. So that means that this is less than or equal to this, And if you notice from this expression here, that's a perfect square trinomial. It's the square of this binomial, which is what we wanted on the right-hand side. So to get the inequality, you just take the square root of both sides of this inequality. So the square root of this is equal to the square root of this. The square root here cancels with the square, and you get the inequality that you want. All right. Part B, they want us to prove the triangle inequality. So that's this inequality that they have written here. And then they just say interpret this geometrically. The name is, well, I'll talk about it after we do the proof. For part B, it's once you have part A, it's almost trivial to show this. You just have to know one little trick. On the left-hand side of the inequality here, let me just go back up for a second. So here, notice you have x3 minus x1. I can write that as x3 minus x2 plus x2 minus x1. Notice that it's like I'm adding 0, so it doesn't change the value. And I can do a similar thing here, right? I can write this as y3 minus y2 plus y2 minus y1. Again, it's like I'm adding 0, so it doesn't change the value. Okay, so that the square of the left-hand side in part of that inequality in part B looks like this, where I'm just using that trick, right? I'm adding 0 inside the parentheses here. And then plug this value in the triangle inequality. Let me just scroll up a second. Plug this in for x1 here, plug this in for y1 here, plug this in for x2 here, plug this in for y2 here, and same thing down here, and you just get the inequality. So you once you have part A, there's virtually no work you have to do to get the triangle inequality. All right, so that's the solution for part B. And let me just talk quickly about what the geometry says. It's called the triangle inequality because if you have a triangle, let's say this is L1, L2, L3, the triangle inequality says that the length of any one side of the triangle will always be less than or equal to the sum of the lengths of the other two sides. That's why it's called the triangle inequality. Right? Okay, next problem. 15, draw the graph of f of x equals ax squared plus bx plus c. And he gives a hint here to use the methods of problem 118. The methods of problem 118, we also did this problem. Again, you can see the solution that I did for 118 in the videos for chapter 1 in Spivak, so you can take a look at that if you want to. We can write this as this, which tells us that this parabola has or this function has minimum value at this point. So this is the minimum value or the maximum value if the parabola opens downward. It happens at this x value, and also that the roots of the equation where y is 0 are equal to this, which means that this has x intercepts at these two values if those quantities are real. That's what it says basically. And then going back up, so we just look at the different cases of when what the discriminant is for the from the quadratic formula. So case 1, if the discriminant is positive, you get a parabola that either opens up or downward based on the sign of A that has two real x-intercepts. Okay, for case 2, if the discriminant is equal to 0, you have exactly one real root, which is the x-intercept. And, they open either up or down based on the sign of A. And if the discriminant is negative, then you have no real roots, which means that the graph of the parabola never touches the x-axis at all. So it either lies completely above the x-axis if A is positive, or completely below the x-axis if A is negative. Right, so that's essentially the solution there. Next problem was number 17, which was a graphing problem as well. The symbol, I don't know if you guys are familiar with this. This is called the floor function, or sometimes it's called the greatest integer function. This is the red floor of x. denotes the largest integer, which is less than or equal to x. Draw the graph of the following functions. And the reason I did this one is because he says in parentheses here, these are quite interesting and several will reappear frequently in other problems. So since he's going to be referring to these later on in the book, I guess, I wanted to do them just so we have, have them to refer to in this video. So, but graphing them is not that hard. The graph of the floor function looks like this. Graph of x minus the floor of x looks like this. It's a function with period 1, and you get these little line segments here that just repeat every distance of 1. Right, then for part 3, take the square root of the function in part 2, and that just turns the line segments into pieces of the square root function. So this is a part of the square root function, and it just repeats with period 1 also. Right, the graph of floor x plus root x plus floor x, what you do is you take each of the pieces here, and just for the next one, you just shift it up by 1. So you get this sort of like bumpy looking function that looks like that. It goes on forever. Right, the graph of floor of 1 over x looks like this. For x values that are greater than 2, the floor will always be 0. So that's why I have the heights here are all 0. Between 1 and 2, the floor will be 1. So you have a horizontal line segment between 1 and 2 on the x-axis. Between 1/2 and 1, the height will be 2. So you get this line segment between 1/2 and 1, and so on like that. So from 1/3 to 1/2, you get this line segment and so on. And then the graph is an odd function. So if it looks exactly the same, it's like the mirror reflection through the origin on the other side. Right, so that's what the graph of that looks like. And then the last graph is the graph of the reciprocal of that function. So at the points where the function in part 5 is 0, the function's not defined. And for the other intervals, it's just the reciprocal of the height for the other function. So it looks like this. Right. Question number 20 is also a graphing problem. Here they want us to graph the function f of x equals, so here we're defining it in this piecewise way. It's 0 if x is irrational, and it's 1 over q for x rational of the form p over q, where p over q is in lowest terms, meaning reduced form, which you could always do for rationals, if you recall. All right, so you can't actually draw this graph. He says draw it as well as you can. You can't actually draw this graph because the rationals are dense in the real numbers. So as you get closer and closer to 0, you get more and more points in between, each of the intervals of length 1. But if I like zoom in to the interval from 0 to 1, it looks like this. It looks something like this, and the function will repeat with period 1. So let me just explain how I got this picture here. Now this isn't the entire picture either, because again, as you get closer and closer to 0, notice the ... here. So for the denominator getting larger and larger, the points get more and more dense as you go along. But I'm not gonna. You can't really draw that, right? So, but just to get an idea of what it looks like, at integer values, the denominator is 1, so the height of the function at those points will always be 1. Where's the... Oh, here you go. So here, the height at 1 is 1, the height at 0 is 1. And then for other values, for example, when x is 1/2, the denominator is 2. So that one takes on a height of 1/2. For all the points in the interval from 0 to 1 that have denominator 3, there's actually there's 3 of them, but or I guess you could think 4, like you could think of 0 as like 0/3, but again, it's not reduced. So the only two reduced points that have a denominator 0 is 1/3 and 2/3. So both of those points get a height of get a point at a height of 1/3. For 1/4, again, there's only a couple places where that happens. For 1/5, there's a few more places where that happens. Just keep in mind, that the numbers have to be in reduced form in order to have the height at 1/q. So it looks something like this, but again, it gets more and more harder to draw the picture, as the y values go down to 0, right? Because the rationals are dense in the reals. So yeah, but approximately that's what it looks like over the interval from 0 to 1. And then to get the entire picture, you just use the fact that this picture will repeat with period 1. So, again, you can't really draw it, but it'll look something like this, and the dots will get um, more and more dense as you get, like I said, as you get closer and closer to 0. So yeah, that's what the graph looks like. All right, question number 21. Part A says the points on the graph of f of x equals x squared are the ones of the form x squared. Prove that each such point is equidistant from the point 0, 1/4, and the graph of g of x equals -1/4. See the figure. I drew the figure down below, so I'll show that to you in a second. If you remember when you learned about conic sections for parabolas, this is called the focus. And I believe the name of this line is called the lattice rectum, I believe. So let's do that. This is the figure that he has drawn in the book. So all I want to do is show that d1 is equal to d2. So using the distance formula, the distance d1 is the distance between x comma x/2. I'm sorry, the distance from the point x squared and the point 0, 1/4 by the distance formula is given by this, which if you actually simplify out, gives you this number here. And if you take the distance between these 2 points using the distance formula, you get this expression here, which is the same as this one. So the distances are the same, right? And that's all they wanted us to show in this one. Part B, they want us to do this in general. Given a horizontal line L, the graph of g of x equals gamma and a point P with coordinates alpha, beta, not on L, meaning that the line is not vertical. So that gamma is not beta, show that the set of all points x, y equidistant from P and L is the graph of a function of the form, the quadratic function ax squared plus bx plus c. What is the set of gamma? What is this set if gamma equals beta? All right, so let's do that down here. Again, I'm just using the distance formula. Actually, I'm using the square of the distance formula just so I don't have to deal with square roots. And when you find the distances and solve for y, that's what I'm doing here. I won't go through the algebra. It's just algebra. As long as beta is not gamma, you can solve for y, and you get this expression here, and which gives you the a quadratic function with these coefficients. Okay, and if gamma is equal to beta, then you get this equation, which gives you that x is alpha. So going just so you can see where that comes from. If gamma is equal to beta, this side becomes 0. This sum is 0. So you end up with that. You end up with this equation. And this is a perfect square trinomial. It factors into x minus alpha squared. And if you set that equal to 0, you get that x is alpha, which is the equation of a vertical line that passes through the point P. And that's the solution if gamma equals beta. Right. Question number 22 is a starred problem, and I forget what he means because it's been a while since I read the introduction. I forget if the star means it's a difficult problem or if it means that it's referred to later on in the text. But it's a starred problem, so whatever that means, this is one of those problems. I just don't remember if it means it's a hard problem or if it's used later on. but let's do it anyway. So 22a, show that the square of the distance from CD to mx is given by this expression, x squared plus m squared plus 1 plus x times minus 2md minus 2c plus d squared plus c squared. Using problem 118, to find the minimum of these numbers, show that the distance from CD to the graph of that line is given by this formula, absolute value c times m minus d divided by the square root of m squared plus 1. So let's do that first, and then we'll take a look at part B. So using the distance formula to find the distance from the point to this line here, I'm using the square of the distance just so we don't have to think about square roots. The distance formula gives you this. And then just simplify everything and rearrange things. And again, it's just algebra. When you do that, you get this. So you get a quadratic function in x where the coefficients are m squared plus 1 minus 2c minus 2md and c squared plus d squared, which is what they wanted us to show. Okay, and then using problem 118, the minimum value of this quadratic function here is given by the y coordinate of the vertex, which is given by this formula here, 4 alpha gamma minus beta squared over 4 alpha. So if I plug the values for those coefficients into the formula, I get this expression here, and notice I can cancel some things once I simplify, multiply everything out and simplify the expression. When you simplify everything, you get that the minimum of the square of the minimum distance is given by this. Take the square root of both sides. You get plus or minus, but this is a distance, so you choose the positive one. And that gives you, when you simplify, the formula that they wanted us to show. Right. Again, if you want to see the solution to problem 118, you can go back to the videos for chapter 1 in the playlist. Right, and then there's a part B. Part B says, find the distance from CD to the graph of f of x equals mx plus b. And this, once you have part A, it's trivial to do this. You just reduce it to the case in part A. So let me show you how to do that. All right, so the distance between the point CD and the line x mx plus b is the same as the distance between the point C d minus b and the line x mx. So you just subtract b from both of these points. So it's just a vertical translation downward by the same distance. So the distances are preserved under that transformation. And then just using part A, the value for the y value for the point is this one. So you just plug that in over here, and it gives you exactly the distance, which is this. Okay. All right, last problem in the problem set for chapter 4, other than the appendices. Again, we have those 3 appendices still to take care of, but this is the last one I did in the exercises for chapter 4 itself. So 23a says, using problem 22, the one we just did, show that the number x prime and y prime indicated in the figure are given by those formulas. So x prime should be 1 over radical 2x plus 1 over radical 2y, and y prime should be negative 1 over radical 2x plus 1 over radical 2y. Let me show you what they mean by x prime and y prime. He gives this picture in the book. So what we have is, so if this is the x-axis, let me do this in black actually. If this is the come on, this is the x-axis and this is the y-axis. The blue axes are just the regular xy axes, but rotated by 45 degrees. Right. So he wants us to show that the new coordinates of the point x, y in terms of the new coordinate systems here are given by those formulas, right? And he's giving us a hint also that this distance here is the length of x prime, the coordinate, this would be the coordinate x prime for the point in terms of the new axes. And the length here is the length of the coordinate y prime for the point xy in terms of the new axes. Right, so we can do that actually using the formula from question 22. Let's do that, and then we'll take a look at part B afterward. Okay, so here I'm just making some definitions. So x prime is the distance from xy to py, and y prime is the distance from xy to x prime, right? In other words, the distance here, right, the length of y prime is actually the distance of this point to this line. Okay, this line has equation y equals x because this angle is 45 degrees over here, right? It's the identity function. In other words, this is 1 times x plus 0. Okay, so the slope in this case is 1, and the distance which one did I just do? I did this distance. So the next one is the distance here. So in other words, the length of x prime is the distance of this point to the point over here, which I'm calling py prime. I'm calling this one px prime, by the way. So the distance of this point to this point is the distance from the point to this line here. And that line has equation y equals negative x, or in other words, the slope is -1 times x plus 0. So here the slope is -1. So using the formula from question 22, part A, we just plug in the values and we get what we want. So here the distance from P to Px prime, using the, like I said, actually, let me just remind you, we're using this formula here, right? That's the formula that they're talking about. Right, plugging in, we get that the distance from P to Px prime is the absolute value of x times the slope of the line y equals x, which is 1 minus y, and divide by the slope squared plus 1 square root. The slope is 1, so you get 1 squared plus 1 under the square root. And when you simplify everything, you get that that's equal to the absolute value of 1 over radical 2x minus 1 over radical 2y. Now this is the distance, not the coordinate. It's the magnitude of the coordinate. The coordinate itself can either be positive or negative, right, for the new axes. So the sign of the coordinate is just whatever is equal to the sign of whatever this thing inside the absolute value is. So that means that y prime has to be equal to this. All right. And then you do a similar thing for the other distance. So the distance from P to Py prime, again, is the distance from xy to the point on the line y equals minus x. The slope of that line is -1. And actually, I just noticed a typo here. This should be -1 squared, but it doesn't really matter because -1 squared is still +1. And then just simplify that, you get absolute value 1 over radical 2x plus 1 over radical 2y in absolute value. Again, this is the magnitude of the x prime coordinate, but the x prime coordinate could also be negative. So x prime is equal to this quantity here. Whatever it takes on the same sign as that quantity, it has that magnitude though. So x is equal to just the quantity 1 over radical 2x plus 1 over radical 2y, right? And that's the derivation of those formulas, which I thought was pretty neat. This problem, because usually when you see these formulas derived, it's done in like linear algebra, and you use trig identities to do it. But I haven't seen it done this way before, which I thought was really neat. It's using sort of like an optimization method, like a projection, I guess. So I thought that was kind of neat. Okay, so that's the answer for part A. And part B says, show that the set of all points x comma y that satisfy that equation there. So x prime over radical 2 squared minus y prime over radical 2 squared equals 1 is the same as the set of all points xy with xy equals 1. So let's do that. All right, so part B, we're starting with the equation here that they gave us. I can plug in the value for x prime and y prime that I derived for them in terms of x and y in the part A. So x prime is given by this formula, y prime is given by this formula. And simplifying that, you get x plus y squared over 4 minus y minus x squared over 4, put the left-hand side over the common denominator of 4, and simplify everything. So if you notice some things cancel, let me actually write that out. So notice x squared cancels with minus x squared, y squared cancels with minus y squared, and 2xy plus 2xy is 4xy, and notice that the 4's cancel. So you get xy is equal to 1, so the locus of points are the same. Right, and that's the last problem in this section. So let me stop the screen share. Okay, so like I said, that was selected problems anyway that I thought were interesting from the chapter exercises for chapter 4. So in the next 3 videos, sorry, next 6 videos, I guess, I'm going to do the appendices for chapter 4. So we'll do the summary for appendix 1, then the exercises for appendix 1, and same thing for appendix 2, same thing for appendix 3. So hopefully I'll be able to finish all of those by the weekend. We'll see if I have enough time to do that. I do have work for the next, today and tomorrow, so pretty much all day. So I don't know how much time I'll have to work on this before the weekend, but I'll get as much done as I can. And once we finish up, everything in chapter 4 here, we'll finally be up to chapter 5 in Spivak, which is the start of the calculus material in the book. And actually, I just wanted to make another little clarifying thing about what we're going to do after that. I know I'm trying to finish Schifrin, chapter 1 in Schifrin and chapter 1 in Simmons, but the material that we just finished in Simmons is relevant to the material in chapter 2 in the Taylor book. And I'm kind of getting the physics bug again. So I think actually what I'm going to do is I'm going to do, after I finish chapter 4 in Spivak, I think I want to actually do chapter 2 in Taylor, and then I'll finish up. There's only a couple things left to do in chapter 1 in Simmons. So I'll finish those up after that, and there's only a couple of sections left in chapter 1 in Schifrin. They're kind of long sections, but there's only 2 of them left. So then we'll finish up that stuff. So got a bunch of good math stuff coming up in the near future, so look out for that. And like I said, the next few videos will be finishing up the chapter 4 stuff in Spivak. So we still have the appendices to do, and then we'll be done with chapter 4. So until that time, well, let me know what you guys think in the comments, first of all. Please do like and subscribe. It helps the channel. I have to get all that stuff out of the way, right? And I'll see you guys in the next video. Until that time, keep learning.